A life cycle assessment, also called an LCA, is a method to measure the total environmental impacts of a product or service across its whole life, from raw materials through manufacturing, transport, use, and end of life. The aim is to compare options fairly, identify the stage with the biggest impact, and make improvements there without shifting the burden to another stage. An LCA follows 4 stages, called goal and scope definition, inventory analysis, impact assessment, and interpretation. In goal and scope, we set the question, choose a functional unit that makes options comparable, and draw the system boundary, for example, cradle to grave, for the full chain, or cradle to gate, up to the factory gate. In inventory analysis, we collect quantitative data on inputs and outputs, including energy, water, raw materials, transport distances, emissions to air, water, and land, and solid waste. In impact assessment, we convert the inventory flows into indicators such as climate change, carbon footprint, energy demand, water use, eutrophication, acidification, and resource depletion using consistent methods. In interpretation, we check data quality, run sensitivity and uncertainty tests, and translate the findings into clear recommendations for design, purchasing, and policy. As an example, we compare 1-liter drinks packaging for a glass bottle, an aluminum can multi-pack, and a plastic bottle, using the functional unit of delivering 1 liter of drink to the consumer. The inventory shows that glass is heavy, so transport energy is high. Aluminum needs a lot of energy for production, but recycles very well. And plastic uses less mass and transport energy, but can create end-of-life pollution if not collected. The impact results can show the lowest carbon footprint for recycled aluminum or lightweight plastic, higher water use for washing returnable glass, and different waste outcomes that depend on local collection and recycling rates. Limitations of LCA include uncertain or missing data, assumptions about recycling rates and lifetimes, allocation choices for byproducts, boundary cutoffs, and the risk of selective reporting that leads to greenwashing. The conclusion is that a good LCA uses transparent data and fair boundaries to guide choices such as material selection, lightweighting, reuse, refill, and better recycling, so the total life cycle impact is reduced.